In section 4.3, we are moving on to a topic called binomial distributions. And binomial distributions are unique and also very helpful as we're going to learn in here in just a minute. First, to determine whether a probability experiment is a binomial experiment. An experiment is said to be a binomial experiment if the following conditions are true. So first of all, the experiment is performed a fixed number of times. You have to decide before you start how many times you're going to perform the experiment. Each repetition of the experiment is called a trial. Number two, the trials have to be independent. That means the outcome of one, remember, does not affect the outcome of any of the other ones. This means the outcome of one trial will not affect the outcome of the other trials. It's amazing that I said that and it was on my notes. Number three, for each trial, there are two mutually exclusive or disjoint outcomes, and these two outcomes are defined as success or failure. Now I'm going to pause here. It's important to realize that success in this case doesn't mean something good, and failure doesn't mean something bad. Success, we just have an outcome that we're looking for, and we will define that as a success, and then everything else is defined as failure. Number four, the probability of success is fixed for each trial of the experiment. And it has to be the same for every, it's fixed. It's the same for every trial of the experiment. So you can't have a probability of 50% success this time and then magically 30% next time. It has to be the same for every trial. So notation for binomial probability distribution functions. First of all, there are n independent trials of the experiment. Remember that n has to be determined before you perform your experiment. We're going to let p denote the probability of success. So that will be a decimal number between 0 and 1, or a fraction between 0 and 1. And then q, that will be our notation for the probability of failure. So that will always be 1 minus p, because that's just everything that's not success is considered failure. We're going to let capital X be a binomial random variable that denotes the number of successes in n independent trials of the experiment. So our lowercase x has to be between 0 and n if we are doing n number of trials. Example 4.9, which of the following are binomial experiments? Letter A, a player rolls a pair of fair die 10 times. The number x of 7 rolls is recorded. So first thing that we want to look at here is they have determined they are going to roll the die 10 times. There is a fixed number of trials. The second thing, since you're rolling fair die, those trials are independent, and also the chances of rolling a 7 are the same every time you roll the pair of die, the pair of dice. Let's see, what else are we looking for here? The number of 7s is recorded. So our success in this case would be defined as rolling a 7. Failure would be defined as not rolling a 7. And that's how you do the success and failure. Success is one outcome that you're looking for, or maybe multiple outcomes, but it's an event, it's a set of outcomes that you're looking for. And then failure is just everything else when we're talking about a binomial experiment. So the answer is yes, this one is a binomial experiment. Letter B, the 11 largest airlines had an on-time percentage of 84.7% in November 2001, according to the Air Travel Consumer Report. In order to assess reasons for delays, an official with the FFA randomly selects flights until she finds that 10 were not on time. The number of flights X that need to be selected is recorded. So the first thing we want to look at is, at least the first thing that jumps out at me is this right here. The official Randomly selects flights until she finds 10 that were not on time. That is not a binomial experiment right away, because remember that for our binomial experiment, there have to be a fixed number of trials, and that has to be decided before you even start. You can't just keep going and going and going with more trials until finally you find 10 of them where they're not on time. So that one is not a binomial experiment. Your percentage, there's probably enough flights that you're looking at that the percentage, those are probably independent events, so that's not an issue. The number of flights that need to be selected is recorded. That's not a binomial experiment either. So this one is just not. Letter C. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. So randomly selects 4 students. That would be a fixed number of trials. There are 4 trials, so N is 4. In a class of 30 students, 55% are female. So here's where these two options come into play. Without replacement, we have a problem, because if 55% of your students are female, let me grab my calculator here. That's an interesting number. That actually doesn't even make sense. That means 16.5% of your students. Let's just change this to 60% of your students are female. So that would mean 18 out of 30 are female. So that would be your percentage on the first one. If you do not replace them, then the second time it would be 17 out of 29. And so therefore, your trials are not independent. So without replacement, the answer is no. This is not a binomial experiment. So let's go on to with replacement. That takes care of the independent issue. So yes, it's independent. We have our fixed number of trials. The instructor randomly selects, and the number X of females selected is recorded. So we could define success in these trials as selecting a female. Then failure would be not selecting a female. So yes, you have your two different outcomes, success or failure. And yeah, this one is with replacement. This one would be a binomial experiment. So in this case, the independence was the key thing, because when it wasn't when it was without replacement, it was not a binomial experiment. But when it was, then it is. When you did replace, then it is a binomial experiment. So continuing to talk about our binomial probability distribution function, the probability of obtaining X number of successes in N independent trials of a binomial experiment is given by this formula. Probability of X, P of X, equals NCX. Now you will remember, hopefully, from our previous classes that this means you've got a combination. And the combination means we're going to find the number of times that this success could happen if we don't care about that this number of successes could happen if we don't care about the order, because we really don't care what order the successes happen in. And so that's why we're going to use this combination of N items. Notice N number of trials taken X at a time, and that is successes. The number of successes that we're trying to find the probability for. Notice then we're going to have P to the X power. P is the probability of success. We defined that earlier, and it will be noted here in just a minute. And then 1 minus P, or you might write this as Q, which is the probability of failure. And that is N minus raised to the N minus X power. That just means it's the number of trials minus the number of successes. So this would be the number of failures. And then for x equaling 1, 2, 3, 4 up until n, where p is the probability of success. So in other words, you could find out the probability of any number of successes, and if you wanted to find all of them, you just go through and you would have to do this for each possible x value. But that's what all those things stand for, and that's kind of a nice pattern. It's actually kind of easy to remember once you do it, but again, we are going to be able to do this on the calculators, so we're going to learn how to do that as well. Our next example, at ABC College, the withdrawal rate from an elementary physics course is 30% for any given term. This implies that for any given term, 70% of the students stay in the class for the entire term. A success, so again, when we do these binomial experiments, we have to be able to define success. So success could be defined as an individual who withdrew. So again, it doesn't mean that it's good. We would consider that probably a bad thing. But success in this binomial experiment could be defined as an individual who withdrew. The random variable x would equal the number of students who withdraw from the randomly selected elementary physics class. So the point of this example is that success doesn't have to necessarily be thought of as a good thing. Success is just what we're looking for. Another example, a trainer is teaching a dolphin to do tricks. The probability that the dolphin successfully performs the trick is 35%. The probability that the dolphin does not successfully perform the trick is 65%. Out of 20 attempts, we want to find the probability that the dolphin succeeds 12 times. State the probability question mathematically. So first of all, we want to define success. We want the dolphin to succeed 12 times. So success is actually they successfully perform the trick. Okay. Next, we're going to find the probability of x equaling 12. And that is basically how we define this. Now, if we wanted to go further and actually set this up with our notation, we know in this case, n, does it say how many times? Yeah, 20 attempts. So n is 20. So we would have 20 c, what are we looking for? 12. And then times p, and p in this case is the chances that they are successful in performing the trick. So p is going to be 0.35 raised to the 12th power, because that's how many times we want the dolphin to succeed, or we're looking for that 12 times of succeeding. Then the q, or 1 minus p, they actually gave that to us. Q, which is equal to 1 minus p, is 0.65, and that would be raised to, well, 20 minus 12, which is 8. So there are 8 times where they would fail then in that situation. And so mathematically, this is the work that we would have to do in order to get that probability of succeeding 12 times. And that would be a pretty small number because the chances of them succeeding are at this point only 35. They've got to do some more practicing. Our next example, a fair 6-sided die is rolled 10 times. Each roll is independent. You want to find the probability of rolling a 1 more than 3 times. So we are going to roll the die 10 times, so n is 10. They are independent, so we can do a binomial experiment here. So let's define our success. We want to find the probability of rolling a 1. So rolling a 1 is our success. Now we want to find the probability of doing that more than 3 times. So the way we define that one is probability of x being greater than 3. So I need to be careful. the success is just the 1, then the part that we're looking for here is we want to find the probability that x is going to be greater than 3. And then this one I'm not going to set up because this is going to take a little bit more work, because we would actually have to do this either several different times to find the probability of 4, 5, 6 of x being 4, x being 5, x being 6, x being 7, x being 8, x being 9, or x being 10. Or we would have to do the complement where we find the probability that it's 0, 1, 2, or 3, and then subtract from 1, which would actually be the easier method. Example 410. According to Experian Automotive, 35% of all car-owning households have 3 or more cars. Suppose that there is a random sample of 20 car-owning households. What is the probability that exactly 5 households have 3 or more cars? So we're actually going to do this one. Let's start by defining. First of all, we've got to have a fixed number of trials. And here is our random sample of 20 car-owning households. This is our n value. Next, the trials have to be independent, which means your probability of success has to be the same every time. And according to experiment 35% of all car-owning households, there is your your probability of success. That's going to be P. Now, we need to probably define success here so that we're paying attention to it. Success is, what is the probability that exactly 5 households have 3 or more cars? So success is having 3 or more cars in the household. That means failure is everything else. I'm not going to take the time to write that. Eventually we might, but right now failure is just everything else. Now, what we're looking for is the probability that x, the number of successes, is exactly 5. So we want x to equal 5. All right. So we know that 20 was our number of trials. That's n. Then we're going to have c. And then we're going to have, we want x to be exactly 5, so that's going to go there. Then again, just following our formula, we're going to have p raised to the x power. Well, we just figured out p is 35%, but we have to write that as a decimal. So I'm going to put that in parentheses here, 0.35, and raise that to the x power, which we already have figured out is going to be exactly 5. Then, now this one they didn't give us. In this next parenthesis, goes q, or 1 minus p. So since we have figured out that p, or we figured out from the situation that p is 0.35, that means q, or 1 minus p, is 0.65. So that's going to go into our next parentheses, 0.65. And then the exponent for that is n minus x. So in our case, and this is the number of failures that we're looking for if there are exactly 5 successes. So that's going to be 20 minus 5, which is 15. So that will be our exponent on this one. So now I'm going to show you at least how to type this into the calculator, and then I'm going to show you eventually how to do it with the whole thing just by typing it into the calculator. So my values moved, but hopefully they're in your notes there. So we're just going to type this in. We're going to have 20, and then we're going to go to the math key and over to PRB. Remember, we did that before. If you're using the app, remember, you just go to that PRB menu and go down and select NCR, and then you'll put in your 20. But after the 20, we're putting in 5. And then we're going to put right times, or actually, I'm just going to put parentheses because that's what I did in my formula. 0.35 raised to the 5th power, and then we're going to have 0.65 raised to the 15th power. And then it said we were supposed to round to 4 decimal places. So in our case, that would be 0.1272. So the probability of, and it's not on my page here anymore, but probability of x equaling 5 is 0.1272 if we round off to 4 decimal places. So that's how we would type in that equation that we set up. So here are the steps that we would use with a calculator to find that probability for a binomial experiment. So to compute these probabilities where p of x equaling lowercase x, number one, we're going to press the second variables button. That's going to be a new one. We haven't used that one yet. To access the probability distribution menu. We will be using it a lot more from this point on, but we haven't used it yet. Number two, highlight binomial, BINOM PDF, which stands for probability, or it stands for binomial probability distribution function, and then hit enter. Number three, with that on our screen, on the home screen, we're going to type in these values. We have to just type in the number of trials. We have to type in the probability of success, which is P, and the number of successes that we're looking for our probability, which is the lowercase x. Then we're going to hit enter. If you're using an older calculator that is not, or one that has not been updated, then on the screen, you'll actually see this, and you'll type in the n and put a comma, which is right above the 7. You'll put in your p value, and then a comma, and then you'll put in your x value. So it'll look a little bit different, but on the app, it's going to look like what you're going to see here on the screen in just a minute. Now, if we want to compute the probability for a binomial distribution where p is going to be your x being less than or equal to a number, so it's not just one number we're looking for, but we're looking for the probability that it's in a group of numbers, we use a slightly different process. Here's how we do this one. The first step, again, press second variables to access the probability distribution menu. But this time we're going to enter the binomial CDF, which stands for a binomial cumulative distribution frequency. And if you remember that word cumulative from earlier, it means we're going to add up everything that's less than or equal to a certain value. And then we'll hit enter. Number three, with that on the screen, we're going to put in our number of trials, the probability of success, P, and then the number of successes, X. And remember, this one is going to give us the chances that we have that number of successes or fewer. So this is going to be used in some slightly different cases compared to the first one where we're looking for exactly X number of successes. Then we'll hit enter. And again, if you're using one of the older calculators that has not been updated, you're going to have that on your screen, and you have to enter these three numbers in separated by the commas, where X is going to be less than or equal to the lowercase x. We're going to go back to example 410, and we're going to do this example again using our calculator. So what we need to write down is that we know n is 20. That's the 20 samples. We know that we're looking for exactly 5 successes, so x is 5. We know that the chances of probability, p, are 35% or 0.35, and that's all the information we're going to need. So what we're going to do is turn our calculators back on, go to variables right here by those arrows. We're going to go, second variable. And that brings us to here, and we're going to have a lot of options. So we're going to have to go down a ways until we get to the binomial PDF. So that is option A here on my calculator. It might be something slightly different on yours. But we're going to select enter. And notice it's going to ask us for these values. Now, I didn't write them down in the correct order for the calculator. I'll try and fix that next time. But the number of trials is 20, n is 20. The p value, remember that is the probability of success. That's 0.35. And then the x value that we're looking for is the 5. That's the number of successes that we're looking for. And we're just going to hit enter. And notice it actually puts it into that format that we saw below if you are using the older style calculators that are not updated to this option. And we get the 0.1272, just like we got before when we did this by hand. So this is going to be handy for us. It's going to be a lot easier to go through that. Now for example 411, we're going to do the exact same type of problem, the exact same scenario, but things are going to change a little bit. So we know that n is still going to be 20. We know p is still going to be 0.35. But here's what's changed. Using example 410, what is the probability that less than 4 of our households have 3 or more cars. So that means we're going to find the probability that X is less than 4. Now we have to be a little bit careful because when we type this into the calculator, that means we're looking for the probability of X being less than or equal to 3. Okay? And so that's what we have to put in now as our X value, because that was our definition, and we're going to use the cumulative distribution frequency for the binomials. So we have to write this less than as less than or equal to 3, because that's how our calculator does this. So we do have to be a little bit careful there. But let's go back to second variables, and we'll go down, and I think this was option B on this calculator. Whoops, I went too far. Binomial CDF is the one we're looking for. And the number of trials is still going to be 20. The chance of success is still going to be 0.35. And the X value, we're going to put in a 3. So this means, remember, less than or equal to 3 households having 3 or more cars. So it changes it into that format. We hit enter, and we get that the chances are, now let's write down what our probability is, or it's right here, actually I already did it. Probability of X being less than 4 is 0.0444. And that is our probability for example 411. For example 412, using example 410 again, what is the probability that at least 4 have 3 or more cars? So I'm going to write this out. This is the probability that at least 4, which means X is greater than or equal to 4. Now, we don't have a way of doing the probability of X being greater than or equal to a number. We only have that less than or equal to. But here's what we want to look at. We just found that the probability of X being less than 4 was 0.0444. This is where we have to pay close attention, because notice these are disjoint events, and in fact they're complements of each other. Less than 4 is everything that's not greater than or equal to 4, and vice versa. So if we want to find the probability that X is greater than or equal to 4, we're going to take 1, which is everything, and subtract all the times or all the probabilities where X is less than 4. And what's left is going to be the times when X is greater than or equal to 4. So if you think about, again, what's going on here, you've got 1 through, well, we'll start out here. Let me say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 20. What we just found in our last example was all the times when X was less than 4. What we're looking for this time is all the times when X is greater than or equal to 4. Whoops, I said 20, but I wrote 12. Okay, all the way up to 20. So you can see that that's covering all the possibilities, and so that's why we can just take 1 minus that 0.0444. So let's figure out what that is. And I'm going to use my answer button here. You can kind of practice using that sometimes. And that's going to give us, when we round it off, 0.9556. So that would be 0.9556 for our probability of X, the number of households that have 3 or more cars, being greater than or equal to 4. Now here are the formulas for us to be able to find the mean and the standard deviation of a binomial random variable. So a binomial experiment with n independent trials and a probability of success p has a mean and a standard deviation given by these formulas. Now, finding the mean is super easy. We probably would never even use a calculator for this. The mean of uppercase X is just n, the number of trials, times p, the number of, or the probability of success. So that one's really easy. We'd probably never do that one with a calculator. This one is still pretty easy. We probably won't do this one, with any special operations on the calculator other than plugging in the numbers. But notice what we're doing here is standard deviation, and you still take n times p, then you multiply by 1 minus p, and if you think about what that is, that's the chances of failure, and then you take the square root of that answer, which means that if we're looking for the variance of this, it's just going to be n times p times 1 minus p. So those are some formulas that we will be using, and that's how we figure those out. Example 413, according to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a simple random sample of 400 car-owning households, determine the mean and the standard deviation number of car-owning households that will have 3 or more cars. Round to 2 decimal places. So first of all, the mean of this situation where, what are we looking for? Of the whole thing. And so we just take 400, which is the n value. And then this is our p value still. So 400 times 0.35 is going to give us our mean. And I'm not going to bother pulling up the calculator on the screen for this. This is just multiplying. You can do that. So 400 times 0.35 gives us 140. So our mean, we don't even have to round it. Our mean of x would be 140. So then to find our standard deviation, we're going to take our standard deviation of x, and it will just be the square root of this, and we're going to plug in our numbers to the formula. So remember, n is 400 times p, which is 0.035, and then 1 minus p. And we have already figured out that that is 0.65 from our past examples, so we're just going to type that in. And again, that's something you can do. I'm not going to worry about putting that up on the screen. So square root of 400 times 0.35 times 0.65. And that gives us, when we round off to our 2 decimal places that they asked for, 9.54. So that would be our mean, 140. That's how many successes we would expect to kind of have out of those 400 trials. And then the standard deviation of 9.54. So calculating the mean and standard deviation of our discrete random variable, first of all, we would enter the values of the random variable in L1, list 1, and then their corresponding probabilities in list 2. So it would require that we go ahead and find all those probabilities if we don't know them already. Then we would press Stat, and then highlight the calculate menu, select one variable statistics, and then just like we've done before, when we've done the one variable statistics, we will get all that information. We will have to make sure that we put in our second L1 or second one to insert the L1. And then for the frequency list, we want to put in L2 as we've done in the past. For example 414, we're going to go through and talk about, we're going to graph the binomial probability distribution with the given values for n and p. Then we're going to comment on the shape of the distribution when n equals 8 and p equals 0.2. So let's make a table here. So n is 8, which means we have values from 0, 1, 2, 3, 4, 5, 6, 7, 8. And with our binomial distribution, we're going to use our calculator here to find these values. So the way we do that is we go to variables again, second variables, to the distribution, and we're going to go down to binomial PDF because we're interested in each one individually. So the number of trials is 8, the p-value is 0.2, and we're going to find the value for 0. And we're going to hit enter, and we get 0.1678. And we'll do all these right away, and then we'll go back and change them. So I'm going to use a little trick. I'm going to go second, enter, and that's going to bring this back up for us. Notice the n is still 8, the p is still 0.2, but this time I want to know about 1. So we're going to get 0.3355. Then we're going to go ahead and second enter. We're going to bring that back up, and this time I want to know about 2, and that is going to be 0.2936. And then we're going to go ahead and second enter, and we're going to put in the 3. And notice we get 0.1468. Second enter. This is just kind of practice. I may do it again the long way so you can kind of see it. 0.0459. And again, the way we're getting that, we go second variables to the distributions, and we're going down to letter A, I mean. And again, trials is 8, 0.2, and then this one we're looking for is 5. It switches it into this form for us, and then we're going to hit enter. So 0.0092. Second variables down to letter A again. We still have 8.2, and now we want 6 for the x value. And we're going to get 0.0011. And second variables, PDF. And this time we want n equals 7, or x equals 7. And we get, now we're at if we round that off, 0.0001, because it would be 0.00008, and so that would round up to be 1, and so I'm going to take a wild guess. This is going to round off to be 0 when we do this one. I'm just going to do second enter again, and I'm going to change this to an 8. All right, yeah, so now we've got 5 zeros, so basically your probability is going to be 0 there. So if we look at this graph, we're going to have, for 0, we're going to have 1.678. So that's going up to 0.2, and so 1.6 is going to be probably around this area right here. For 1, we're going to have 0.33, which is going to be about right here. For 2, we're going to have 0.29. Oh wait, that 0.33 is not right. Let me fix that. Because this would be 0.3 if we estimate that. So a little bit more than 0.3. And then 0.29 is almost up to 0.3. And then 3 is 0.14, so here's 0.1. So 0.14 is going to be about halfway. And then 4 is going to be 0.04, which is almost a half, so that's going to be about right here. And then 0.01 that's getting very short, and then even shorter, and then basically nothing on those last two. It's almost 0. So notice what we're trying to look at here is the fact that since p is 0.2, if we multiply 8 times 0.2, we're going to get 1.6. So notice the highest values are in that region from 1 to 2 because your mean is in that 1.6 range. And so that probability bunches everything towards that 1 and 2 x value, towards those values where x is 1 and 2. And so that groups everything kind of together. Let me put the other graph back on. I have one that's a little bit nicer. So now you can see my points weren't perfect. I tried to estimate as well as I could. But yeah, you can see that graph. And that's the whole point of this is when your p-value is low, your graph is going to be bunched to those lower values. So let's take a look at some other ones. I'm not going to do all the math for all the other ones, but you know now how it would happen. So here's what this would look like if n was 8 and p was 0.5. So notice this time, since it's a 50-50 chance of something happening, success and failure, it's much more evenly spread out. And so you see it's even symmetric. 4 is right in the middle where your mean would be, and we'd kind of expect that. If the p-value goes up to 0.9, notice everything is shifted way towards the top. And so now your highest values are right around 5 and 6, and you don't have much at the bottom, and you have less again at the top. So that would be an n value of 0.9. Notice if you multiplied n times p to find the mu, you're going to get 7.2. And that's, yeah, this even seems a little high to me, 7.2. But according to this, our graph should be right in that area between 6 and 7. But we're getting 7.2. That seems a little weird, but maybe my picture's wrong here. But this is the picture we've got, so we're going to go with it. Then notice if we change this, now the p-value is 0.2, still like the first one, but now n is 4, and so that shifts everything again way to the left because your probability for success is very low there. And so the outcomes tend to be in that 0, 1, and 2 range. Just a few in the 3 range and hardly any in the 4 range. Now, where do we use binomial probability distributions? For a fixed probability of success p, as the number of trials n in a binomial experiment increase, the probability distribution of that random variable x becomes bell-shaped, which means it is symmetric and it's the values are grouped towards the middle, and then they're very low on the outsides. As a general rule of thumb, if n times p times 1 minus p is greater than or equal to 10, and remember what this is the variance. We saw that earlier. That's the variance. If that variance is greater than or equal to 10, then the probability distribution will be approximately bell-shaped. And what that means is you've got a high enough number for n that it gets you into that bell-shaped region. That is the end of section 4.3. You're going to have those 9 graded problems. Make sure you practice using your calculator on these because that's going to be really helpful for you as you do these problems rather than trying to do everything by hand.